So for our final example, before we really get into the course, let's look at a problem involving documents. So we have two documents and our goal is to find out how similar they are. Right? So are these two documents really variations of the same thing? Now there may be many different scenarios where this problem is interesting. So one question may be for plagiarism detection. So it could be that somebody has posted an article in a newspaper or on a website and you believe that this author has not really written the article themselves, but they have copied this article from somewhere else. Or if you are a teacher in a course, you might be worried that two students have submitted the same assignment or one student has copied his assignment from some source on the internet, right? So by looking at how similar, if you can measure how similar two documents are, you can try to quantify this notion that somebody has copied from somebody else. Now, it may not always have a negative connotation like this. It might also be to look at some kind of things when some people are writing code, typically if you're writing programs for some application, over a period of time, documents evolve. In this sense, the program evolves, right? So people add features. Now you might want to look at two different pieces of code and try to figure out what are the changes that have happened, how similar they are, how different they are, what are the actual changes that have happened. Another place where there is a positive notion towards document similarity is to look for web search. Right? If you ask a question to a search engine and it reports results, typically it tries to group together results which are similar because they are not really different answers. Now, if there are 10 different copies or similar copies of a document saying more or less the same thing, and these show up as your first 10 search results, then another document which will be highly relevant and quite different from these will now be lost to you because it will be off the first page of searches. So it is useful to be able to group together the results of a search query by similarity so that the user is actually presented with an effective choice between different answers to the search query and not just a large number of variations of the same answer. So if this is our motivation, we need a way of comparing documents. What is a good measure of similarity of documents? Now there are many different notions that people have come up with. Obviously it has to do something to do with the order of the words and the choice of letters and so on. But one way of quantifying the distance between two documents is to use what is called the edit distance. Namely, how many changes do you have to make to transform one document into another document, right? And by edit, we mean supposing you actually loaded the document in a text editor or a word processor. Okay, what would be the kind of things that you could do? Well, we could limit, because you could of course block out and delete the entire document and then cut and paste another document and say I did it in 2 steps, but this would be kind of cheating. So we have to limit what operations you do so that we have a uniform way of counting this. So we could say that edit involves how many characters you change. Right? So each step of editing will either add or remove a letter, and perhaps we can allow you to replace one letter by another letter and call that one change. Okay? So now we want to count these as our basic steps, adding or removing a letter or replacing one letter by another, and find out how many steps it takes to edit one document to make it into another document. So the minimum number of edit operations will then determine the distance. Now the question that we have as an algorithm problem is, how do you compute this minimum distance, right? How do you decide what is the best way to edit one document and make it another document? Of course, there is always a trivial solution like that block cut and block paste. You can just delete all the letters and then type in the new document. So there is a brute force way of doing it, but this is not likely to be the best possible way, right? So you can also try out all possible delete and insert sequences and see which among them gives you the best solution. But all of these are very inefficient kind of solutions. So again, we can go to this question of decomposing the problem. Right? So supposing our first goal is to just make the first character of the two documents the same. If they're already the same, we leave it and go on. If they're not the same, well, then we have two options. Right? We can either transform the character, the first character, to be equal, or we can insert a character in one of the two documents. Right? So supposing the first document starts with an X and the second document starts with a Z, either we can say we do one operation to make X into Z or Z into X, or we can insert an x before the z, or insert a z before the x. Okay? Or you can delete the x, but then we don't necessarily get the same argument. And then once we have done this, once we have made the first character the same, then we can recursively try to fix the rest of the document. So now one of the difficulties that we face when we do recursion in this manner is that the same subproblem becomes up for solution many times. So a typical example of this is the recursive solution to finding the nth Fibonacci number. So the Fibonacci numbers are defined, it's a very classical sequence. So the first two Fibonacci numbers are 1 and 1. After this, you get the next Fibonacci number by adding the previous two. So after 1 and 1, the next one is 2, which is 1 plus 1. The next one is just 3, which is 1 plus 2, and so on. 5 is 2 plus 3, and so on. So in general, the recursive relationship is given by the fact that Fn is the sum of the previous two numbers, n minus 1, n minus 2. And then you have, as a base case, that the first two numbers, f1 and f2, for which n minus 1 or n minus 2 may not be defined, for these two numbers, the value is 1. Now the problem is that when you apply this recurrence directly, so if you try to compute the 7th Fibonacci number, for example, it will say, okay, for this I need to compute f6 plus f5. But if I then recursively apply this for f6 and f5, we find things like f4 coming up twice. Right? So we have an f4 which comes here and an f4 which comes here, because when I do f5, I need to apply this recurrence. When I do f6, I need to apply this recurrence. So if I naively do it, I compute f4 twice, and in fact, when I compute this f5, I actually get another f4. Okay, so I'm computing f4 a number of times, f3 a number of times, and so on. So this is really an inefficient way to calculate it. Whereas if I just do it, for instance, here, I get 1, 1, 2, 3, 5, 8, 13, 21, and I find that the 7th Fibonacci number is actually in this sequence is 30, right? So there is intuitively a very fast way to do this. The recurrence is respected, but if I do it recursively, I end up solving a lot of problems again and again. So how do we get around it? And this is what we call dynamic programming. So dynamic programming says, do not compute the same subproblem twice. Okay? Whenever we solve a problem, if we have found f of 4 before, just look it up, store it somewhere, look it up, and make sure that you don't do f4 again and again. So this is one of the techniques that we have seen in the beginning that we are going to do in this course, and it's important that when we break up subproblems, problem into subproblems, it's not always the case that these subproblems can be solved efficiently unless we look slightly more deeply into the structure of subproblems and make sure we solve them in an effective sequence. Now, as usual, this problem of the difference or similarity between two documents can be at many different levels. So we are focused on the words, the actual text, okay? But if we don't really look at the sequence of words, okay, we just want the set of words, then they might be far apart in terms of edit distance because we need to rearrange the words. But the content, if we just measure in terms of what types of words are there, this might give us an accurate understanding of the meaning of the document. So if you actually search for a document in a typical search engine, you will often find that the words that you ask for may not occur together or may not occur in the sequence that you mentioned them. It will just find documents which have that collection of words. Okay? So this is very useful for web search. Okay? And the other thing that you might want to do is measure similarity of words in terms of meaning. So if you search for a document which contains the word car and there is another document which contains the word automobile, it might be a good idea for the search engine to report the documents containing automobile because automobile and car are essentially the same thing. Okay? So like the other examples we have seen before, there can be variations on the problem, and the solution that you have for the original problem may or may not be valid for these variations. So there is always a whole space of new and interesting problems to solve in all these things.